So this is the last machine learning class, and starting on Tuesday, the final exam's available in all my classes. The last class of the semester will be Monday. I'll be there to help people that may have questions, but that's it for lectures or classes. It's just final exams after that. So we're down to this chapter 13, and let's take a look at that. This is all technical details about TensorFlow, but we'll see how interesting it is. Took me a while to get this ready. So we'll talk about the TF data API and the TF record format, and then preprocessing and the datasets project. So what we've done before, when we imported that California housing data about districts in California and how much housing costs, we used pandas and scikit-learn. Those are the things that would just read a CSV file and then take the data out of it. So that's scikit-learn, and scikit-learn has simple methods to split the data into training set and test sets. So it's got convenience features like that, and that's good. But if you want a more powerful library to load and preprocess data sets because you have multiple files you want to combine or you want to do more preprocessing on them, then you can use the raw TF dataset. This can read multiple files in parallel with multi-threading and many other techniques. And it can also, as we'll see, you can tell it to load the next batch of data while another batch is training, because you might have multiple processing devices such as CPUs and GPUs in your machine, so it can keep all of them busy, and that will speed things up. It can also handle data sets too big to fit in memory, so it has these advanced features. Now, when you save the data set, the native format to use is this TF record binary format that supports a lot of useful things like compressing data and reading from SQL databases or from Google's BigQuery. So if you go to the data set, and here I just create a data set from tensor slices of x, and x is just using the range of 10, which will just give me numbers from 0 through 9. So here I'm just storing, it's a tensor, which is just essentially a vector, and I once read an explanation of why a tensor is different than a vector, and I can't remember. It's a list of numbers with some subtle difference that I can't remember. I thought maybe perhaps that it goes up to high dimensions. But anyway, this is just one-dimensional, numbers 0 through 9. And you can make a dictionary where you have category A with 2 groups of numbers, 1, 2, 3, and 4, 5, 6, and a category B with 7, 8, and 9. And so now it will take the first element of this as the first part of the 1 for A, and the 4 for the second bit of A, and the 7 for B. So it'll group these together, the first out of each group, the second out of each group, and the third out of each group to make separate tensors. This is one way to load immediate data into the thing. And so after you've got some data in there, you can repeat the input data. So here you input the numbers 0 through 9, then you repeat it 3 times. So now you have 30 total elements, and then you batch it in groups of 7. So here you go, 0 through 6 is the first 7, 7 through 9, and the sum of the next bit is here for the next 7, the next 7, and the next 7. 4 groups of 7 is 28, so the last batch has only 2, because you run out of data. So that's how you use repeat and batch. And here's how it looks in a little diagram. So you have tensor coming in from slices, you repeat it 3 times, then you batch it in groups of 7. All right. You can use maps to do some kind of computation on the data. You have to use this crazy thing called a lambda function, which is another one of those things. I must 3 or 4 times have read an explanation of what a lambda function is, and I can never remember it. It's some kind of weird meta function, a thing people use in Python. There's a bunch of these things I always avoid because they're too confusing. It reminds me of this C has this feature where you can do an if-then statement with nothing but punctuation marks, and I never use it because it's too hard to remember and understand. But anyway, lambda function, this is how you double all the data. So you use a map, and this will just take the existing data point x and turn it into x times 2. And you can have filters. Filters will let you filter the data according to any condition, just like, say, a Wireshark filter would do. So here you can say, take the sum of the data And if it's greater than 50, keep it. Now remember, we had 5 sets of data here. And you can see this one is not going to add up to 50. It's only got the numbers 1 through 6. Some of the rest of these will probably add up to 50, the ones that contain big numbers like 8 and 9, I suppose. The last one is clearly not going to add up to 50. It's only got 17. So we had 5 datas, but when you take the ones that only go over 50, we only get 3 of them. So this could be any kind of condition you want. This is how you would filter your data for certain conditions. And you can do take to just pull a few items. So if I go to my data set and I take 2, then I get the first 2 tensors of the list. All right. And shuffle, of course, randomly mixes the instance. And if you want to have a random process, but you want it to always choose the same random numbers, then you can, as we've done before, you can specify the seed. And then it will always start from that seed. So it's a pseudo-random series based on a seed. If you want truly random numbers, then you cheat it from something like the system clock. And that would be more random, although not perfectly cryptographically unpredictably random like you might need for cryptography. But anyway, all the projects we've done in this course, we've always specified the seed because we want to have reproducible experiences in students doing it. And then interleave is something that will read multiple files. You can read a whole series of files and mix them together to make a new data set. So you got, supposed to see interleave in here somewhere. There it is, file path dataset interleave, and then again you use this lambda function to specify something to do to each file path. All right. And then you can pre-process the data. You can write your own preprocessor. Here's one that will take the x minus x mean over x standard deviation. So it'll give you this score, the number of standard deviations away from the mean, which is, of course, a normalization process we've talked about before to make every layer of your model have the same value, the same significance. You often weight things so that they are in a score like that. All right. So you can put all that together. Here you read a data set, and so it's going to list the files from file paths, then interleave them to breed them in, then map them, and then shuffle them, and then put them out in batches. And it's also going to use prefetch that we're going to talk about, which is a way to keep things efficient. So this is what it looks like. List the files, interleave in all the data from these different files, cycle through them, then go down and pre-process them, shuffle them, batch them, and then prefetch them so your learning will be fast. And that's what prefetching is. Prefetch causes it to load the next batch while the previous batch is training, and that way the CPU can be busy loading the next batch while the GPU is busy training, and that would make it perform better. So without prefetching, you'd prepare a batch and train a batch, prepare a batch and train a batch. With prefetching, you prepare a batch while it's training, this one's preparing the next one, and so on. And if you have multi-threaded loading and pre-processing, then you might use more than one core of your processor, more than one thread, so it's even more efficient. All right. So with Keras, you can read them in with a CSV reader and just train them with, you compile the model and fit the model, and then evaluate and predict from it, like we talked about. This is what we've done in previous assignments. But you can make a custom function, and this can speed up training. You could compile it to take more steps per execution, and that would process multiple batches at once. So you can write a more complicated function to customize it if you have to do something more complicated or if you want to make it more efficient. And so the binary TF record format is its preferred format for storing data. It's just got a series of records. They can have varying size. It has the length of it, and then for some reason a CRC checksum of just the length, and then the data, and then a checksum of just the data. That seems kind of silly to me. Seems like one checksum would do for both, but for some reason they check them individually. And a CRC is just a very simple hash function, simpler than MD5. It's only, I think, 32 bits long. It's not very cryptographically secure, so it is not difficult to spoof a CRC checksum, but it does serve to detect if you just had a data corruption error where your storage device flipped a bit. So you create a file here with write. You make a file and just write to it, and you can make a file. You can read from it with TF record data set, and then you can output the data from the file. You can just put out the I think just the shape here. All right. I guess it puts out the record. I don't quite understand. I guess TF is here, then tensor. Oh, this is using that Python convention that if you just refer to a variable and you don't say what to do with the variable, it will by default just print it. Okay, that's what's going on. So it'll print this item. All right. And you can compress the files. As I said, you put in a compression type gzip, and it will compress it just like most web pages are compressed when you load them over your browser. And when you read it, you tell it it's compressed so it knows it should unzip it. This is really important if you have to store really large amounts of data, which is quite common. I know, for example, Splunk does this. Splunk stores compressed data because it has to store all these log files. By the way, there was a news article that came out last week about how federal agencies are not meeting the recommended security procedure of having good log storage. And one of the federal agencies, I guess a fairly large one, said, you know, we produce 40 terabytes of log per day. So it will take an enormous storage system just to store all that data, let alone searching through it and using it. So that's a consideration. All right, so protocol buffers. Apparently, the original purpose of TF record files was for protocol buffers, which store general serialized data. Not that different than what someone was asking earlier about what you should use instead of Wireshark. If to store arbitrary network data would be a similar problem. So this is a technique developed by Google in 2001. In a proto file, you have the definition, and so it might look like this. Here's how you'd store a person. You'd have a string for a name, then some kind of ID, and then an email. And this is repeated, meaning you might have multiple emails. So this is one possible data format: a string item, then an integer, and then an arbitrary number of email messages. So you can make your custom TF record files this way, but in fact, in TensorFlow, the commonly used ones are already defined, and you don't have to define and compile your own. So you can create a message. Now we defined a person. We can import a person, and so it has a name, an ID, and an email. And then if you print it out, you see that. Then you can read and modify the field. We could append another email to it. And then you can serialize a record. Instead of having these separate fields, you can make one binary blob containing all the data. This is how a whole lot of protocols work. And I must say it caught my attention because there are an enormous number of serialization vulnerabilities. Java serialization had this problem, and many others, where you serialize something and now you can make a malicious serialized thing which is has unexpected results when unserialized. We're not worrying about that security issue here, but that's the first thing I think of whenever I see serialized records. But anyway, you serialize it, and now you have this single binary blob that you see has a carriage return and a and then 05 must be some kind of marker of the type of field, then the name, then a line feed, and some kind of marker here, 1A07, and an email address, and then 1A7. So I'm not quite sure what these binary things are. They must be delimiters from one field to another. But the point is you have one blob of binary data, which includes everything. The name, the email addresses, and I guess this must be the 123. This 101A must be 123 in hex or something like that. Oh, 1A is one, no, I'm not understanding actually where the 123 went. I don't think that's 1A. So somehow the 123 is encoded in here. You see, you read the email addresses and the alias, but the binary format they use to store that number is not obvious. All right. And so example is the main protocol buffer used in TF records, and it just contains a list of named features that are repeated. So that's a simple way the feature can be byte strings, floats, or integers. So this does seem like a terribly generic format that would do for almost any kind of data. And so here's a message protobuffer, so you can put in as many bytes as you want, as many floats as you want, as many integers as you want. So, all right. And so here we create a person. I guess, in the example format, not in the person example, so we're going to put in a name, an ID, and emails down here. And we can then serialize it and write it to a TF record file. So that's what's really going on in the background. We save and restore data. And so you can load it and parse it. You describe the features, and then you parse it along with your feature description. So it will now unpack it, and you can see the output here. It has the ID, it has all this boilerplate stuff, tensor, shape, D-type, and here's the number, 123, and then here's Alice at the end, and I think even the email is supposed to be in here somewhere, although it's mighty hard to find in this layout. But anyway, you see it's got multiple copies of the same record just so we can see an example here. All right, let's try a Kahoot, which I should have up here, and I do. Get this cleaned up. (13A). I'll wait till the end of the song. Oh, okay. Just as well. All right, so what's the format used to store data for machine learning? Yeah, that's TF record, and I see Shu's comment saying the designers of that format with the CRCs are thinking there will be integrity issues on the data when it's spread or is distributed. And yes, apparently, they are worried about serious integrity issues, more than I would have expected. Yeah. All right, so which method will keep the records that satisfy a condition? Yeah, it's filter. Good. Just like a Wireshark filter. All right. And what method loads the next batch while the current batch is training? Just to speed things up. That's prefetch, a good name for it. And how are errors prevented? Yep, with CRCs. All right. All right. All right. So in Keras, there are a lot of layers to pre-process the data, and this way you can normalize features so that they don't get too large or too small and therefore have an inappropriate significance. You can handle categorical features, like we've seen this before. In the California data, there was an alphabetic field that said something like near the bay, inland, beachfront, things like that, resizing images and so on. Now, you could modify the original data and just write Python scripts to do it, or on the fly while loading it, or with pre-processing layers inside your model. And they have different advantages, but doing it with pre-processing layers is the most advantageous, because then if you get more data in the same format, you can just run it through. You aren't going to have to remember to automatically, to externally pre-process that new data. So that you have your raw training data, and then you feed it into your neural network that includes the pre-processing layers. Then when you deploy it to production and you put in new data, you can just feed in new data in your raw format without having to add your own manual pre-processing to it. It's already built into your model to include the pre-processing. So you can pre-process it just once and then train it with the neural networks. This is the other way to do it. You can have the pre-processing layers separate, which is probably what you want to do. You certainly don't want to keep pre-processing it again and again in each step of learning. You want to just go through some kind of pre-processing and then train on that model. Would be the logical way to build your model. There's a thing called a discretization layer, which, as you'd imagine, this is sort of like analog to digital conversion. It takes data in some other format and turns it into certain discrete entities. So it's going to take a numerical feature and turn it into a categorical feature by putting it in bins, just like a histogram. And so this is useful for features with a unusual distribution or a nonlinear relationship to the target, where you don't want, say, you got features that go from like 0 to 10, but there's also features that go from 1,000 to 10,000. You don't want them to count 100 times as much. So for example, age. You've got the age of people, and you, as you often do in, say, politics, where you rate the age of voters, you don't just keep track of every age, you just group them into bins. Less than 18, 18 to 50, or 50 or more. And so here, we're feeding in a bunch of ages, 10, 93, 57. But after we do discretization with those boundaries, then it just turns into numbers 0, 1, and 2. So this is young, 0, which is below 18. Here's old, which is over 50. And the ones are the ones in the middle. So now you've got bins, just 0, 1, and 2. All right. Now, if you pass those category identifiers directly through to the model, then it's going to think they mean something numerical. So it's going to think the 0 to 2 is a more significant difference than 0 to 1. In fact, twice as significant, things like that. And you probably don't really mean that, since these bins are just arbitrary labels. You don't really want it to interpret the numerical difference as something you should do math on and give meaning here. So you put it through category encoding. What would be better to do something like one hot encoding, where there's just a 1 in this row for the young, 1 in this row for the middle age, and 1 here for the old. So it does not have some interpretation that there is some meaning to the difference between this and that. It's just a different category. All right. You can also have multi-hot encoding. For example, if there were 2 age categories, like say the age of a person and the age of your house, or something like that, then you'd have 2 possible numbers going together here, and then you might have 2 categories activated here, that sort of thing. All right, then you have a string lookup layer. Now what this is going to do is you feed in a list of strings, and you feed that into string lookup, and you define a string lookup layer, and then you adapt it to the cities. What it's going to do is map numbers to these cities. And now when you map cities, it's going to say Paris. Oh, I saw that. That was number 1. Yeah, I think it makes them and then puts them in descending order of popularity. So Paris is the most common, so it calls that number 1. And then Auckland is number 2 and San Francisco is number 3, or vice versa. Looks like Auckland became number 3. And then Montreal, any unrecognized cities, encode as 0. So this is just a way to take string data and turn it into arbitrary numbers, sort of like binning. And you can also then do one-hot encoding if you like. If you specify output mode one-hot here, it'll automatically turn it into a one-hot array, which is probably what you really want, because once again, you don't really want it to do some kind of number, comparing number 1 to number 3 and deciding that the difference between Paris and Auckland is 2 and the difference between Auckland and Montreal is 3 and that number means anything. That's not really representing anything meaningful about the data. It's instead better represented with one-hot encoding. And then you can have hashing. Now this is not the hashing you think about in cryptography where you hash something in order to recognize if it's changed, like an MD5 hash. This is the hashing you'd find in normal computer science to do like where leveling. If you have a bunch of data coming in and you're setting it in some kind of database and you want it to be efficiently stored and efficiently retrieved, you want to create a pseudo-random map so the data gets sort of evenly spread throughout it. That's what this is doing. So it will generate a hash to randomly sort things into the bins. So if you do hashing with a number of bins equal to 10, then it will sort the cities that come in into bins. And here, there are hash collisions, of course. You could have as many cities as you want. It's going to arbitrarily put them in 10 bins. So 2 different cities may end up in the same bin. In here, Tokyo and Montreal both end up in the same bin. Tokyo is in bin 1 and Montreal is in bin 1. So this is just a way to randomly but reproducibly sort things. A little lost on the purpose of the hashing. Well, the purpose of hashing is just to evenly distribute data that comes in. And the way I've seen it used is when you're designing a database, like in the Mac file system, there is a thing called a B tree, which is how you store files. So each file has some kind of identification number, and each layer of the file system, as you go down through folders, the files are just sorted into bins. It's a way to efficiently sort things. It turns out, if you were to say, sort files by the name, alphabetically, and put the A's in one bin and the B's in another bin, then if A is a more common letter, you'll have a whole lot of files in the A bin, and searching through that bin will take a long time. What's better is to take the file's descriptor and put it through a hash, so each file is sort of randomly and evenly distributed across various values. And now when you do a search, it really will be the log of n operations to dig through a tree. That's what a B tree does. You sort through a certain number of categories, and then you go to the subset and sort through a number of categories. So if you had something like an MD5 hash, you would sort by the right character into 16 bins, and then sort by the next character into 16 bins, and the next character into 16 bins, and therefore it would only take you a number of steps proportional to the logarithm of the length of the hash to find something. That's the idea. It's just a way to load balance, essentially. And in this case, it would be a way to take data that you're not sure what to make of, and you're just sorting it into bins, and you don't have any way to understand what to put them in, so you just randomly put them in bins. The end result will be relatively like a random forest. We talked about those before, a random decision tree, where you just have an arbitrary, randomly pick boundaries and sort things into categories. All right. Yeah, both a key for searching and a value. There you go. Yep. And ignores got it. All right. So now you can encode categorical features. So now if you have, this is going to make a dense representation. So if I have a vocabulary of 50,000 words, and I used one-hot encoding, I have 50,000 dimensional sparse vector, which is hard to deal with. Yep, that's good. Jude's got it too. All right, so another way to embed it would be a smaller dense vector with only 100 dimensions. And so, again, very similarly, you have 50,000 words, but you're going to sort them into just 100 bins. And so how do you know what words belong in which bin? Well, you put them in randomly, and then if you have some measure of accuracy, you can train them by gradient descent. So what will happen is you would have your bins, and then you would measure some kind of efficiency, and hopefully you would get them down to meaningful groups. That's the idea. This is just a general idea because, of course, in our case, the data really came with these numbers on it. But if it came with some other member like latitude and longitude, then perhaps with training you would discover that these are the significant things used to capture it. And I'm not understanding exactly how this works, but it seems to me rather like that process of dimensionality reduction where you find the principal component axes. You would have a high dimensional space and you would discover which actual dimensions are meaningful this way. And another one is word embeddings, which really do happen with large language models. So word embeddings of similar words tend to be close, and so even the distance is kept. So man going to king would be the same vector as woman going to queen, and so on. And this is when you get a word embedding that's trained up to actually match the meaning of the words, which is the kind used in large language models, and a giant leap forward. So you can embed a numerical field. So we're going to have an embedding layer, and we're going to stick in 2, 4, and 2, and it's going to turn a 2 into this two-dimensional vector, and a 4 into that two-dimensional vector, and here's another 2, so it has the same vector. So when you first do embedding from one dimension into the output dimension, you're going to get random values for each of these. But if you have some kind of measure of the accuracy of this, you can train it with gradient descent and optimize it. All right, so if you want to embed a categorical attribute like this, near inland, near ocean, near bay, then first you do string lookup, and that's going to turn these into numbers, and then you do embedding. And so that will embed these into just two-dimensional points, which you can then train on. And this, I think, is the code that goes, is going to simulate this, where these optimize, but it's a little hard to understand because I don't think you have other strings you're going to try and match it with. So I'm not quite getting it. And embedding should be just a vector. And embedding can be in any dimensional space, but it should be a lower dimensional space than the original data. Yeah. All right. These are a lot of good questions, and I'm not sure I've really got it all that much straighter than you folks, but anyway, that's the general concept. All right, so now if you want to handle text first, you can do text vectorization, you can use text library or pre-trained model components. So let's talk about text vectorization. What this does is, by the way, almost completely useless, so I'm not sure why they bother. But you have some training data, like these 4 sentences, and what it does is ignore all the punctuation marks, split on white space, so this is 2 and B. This is also 2 and B. This is the B 3 times, so it numbers the words, and then it encodes unknown words as ones. And again, I think it sorts it into the most common word, which is clearly B here, and the next most common word is 2. So B is number 2, 1 is for unknown words, and 0 is a padding bit. So the most common word is B, that's 2. Then it gives the other ones here. So now when you encode this, it's going to say B is word number 2, good is number 4, and the second one here, so here we are. V is number 2, good is an unknown word. It wasn't here, so that's a 1, and now I'm going to pad it with zeros, so it's 4 across. The next one is question B or B, so that's going to be question B or B. Those are all known words, so it gives them numbers, except the or. The or is unknown, so it gets a 1. So this is a way to categorize words. The thing is, I think this is miserable because now that we have experience with large language models, we know we can do much better because this is just treating these words as meaningless things with no relationship to each other and no connect, and that is a really pretty miserable way to do it. The only thing I think makes sense to sort this way would be something like human last names that really have no pattern and no relationship. For actual meaningful words, you want to do better, which is what we'll do. Anyway, you can then encode it with, you can either counter the words or multi-hot, or you can do this thing where you rate them by the frequency of the term and the inverse document frequency. So what that means is you will weight things if they appear more often, so that they I'm not quite sure we care about this, but the words that are rare in the document are uprated. That's what this term does. So the point is you'll get larger values. And I can't remember the details here. These two things seem to contradict each other. I've forgotten the details already. But anyway, I wasn't very interested in understanding the details of this one because it seems pointless because the one that's coming up is so much better. And this is the one, of course, using real large language model components where it's actually learned the meaning of these words and how they compare. You download a pre-trained model as used in things like ChatGPT 3 or 4, and now it actually has the relationships of meaning near each other. So an elephant is near a mastodon because it knows those words are compared. Such assigning is just like assigning ID numbers to the words in a real-world English dictionary. Well, it is, but only if you don't care about the actual meaning of the words. And the problem is now we have pre-trained large language model components that actually have encoded the meaning of the word, which is so much better. So that's what this will do. All right. And so what you do is you go online to like Tensorflow Hub one place, and you can just download pre-trained models to do many things. BERT for languages, object detection, food classifiers, and many other things. Yeah, the large language models do it this way. Hugging Face also has a layer of them online for language, vision, audio, multimodal, and so on. So you can just download somebody else's open source pre-trained data, but will do much better. And so you can also do other things like resize images, rescale the pixel values, crop just the center part of images. You can do random crops, random translation, and all these random things are, of course, very useful because remember when we were trying to sort out handwritten digits, what if the digit was a little tilted over or something? So you very likely want to try randomizing the images so your model will learn to recognize a number even if it's tilted over. And transformers are doing a lot more than mapping. Yes, they are. They're doing much more. They're actually encoding it as a vector so that things with similar meaning are actually near each other, and things with a relative meaning, like man to king, have a meaningful vector, which is also like the relationship of woman to queen. So that's why it's so much better than this just arbitrarily assigning a number to each word. This system up here is only meaningful if the words don't mean anything, and all you're trying to do is say, if I find a document, a test string with many B's in it, I want to recognize that as being different than one with many word twos in it. So if these were just arbitrary labels, and you just wanted to see which labels are matched, this sort of thing would be true if there wasn't any actual meaning. But if it's actually English sentences like this, then you really should be using one of those downloaded models. All right. And so there's also the TensorFlow datasets project that has many datasets you can practice on. All the projects we've done have used these downloadable datasets where you get things like the images of fashion items and the images of digits to practice on and so on. And there are many, many online datasets you can practice on to develop your models, which is very nice. All right. So that's it. Let's do another Kahoot. All right. All right, so which layer can do one hot encoding here? Category encoding had that ability here. All right. and which layer places similar words near one another. And I think that's an embedding function. Embedding can do that. It can be trained. A little fuzzy on the details. All right, which layer converts brightness to range from -1 to 1, which we had to do when doing the image processing. Well, I think we scaled it from 0 to 1, but anyway, you scale it to some standardized value. And that's rescaling, like turning the volume knob. All right. All right. All right. I got those recorded. Okay. So I'm going to stop this recording.